A very good morning or good afternoon to all of you. I'm Ivan, the Scientific Affairs Manager of Sebia APAC. Today, we'll be talking about hemoglobin variant detection and, importantly, the rules for interpretation. Please feel free to input your questions in the questions chat box. If you do have any questions after this webinar, please also feel free to email me, and my email details are present as follows. Hemoglobin variants, they are also known as qualitative abnormalities or structural variants. Why do we call them structural variants? Because they contain mutations within the globin chains that may change their structure. More than often, the change would involve a mutation to just a single amino acid. However, it's not limited to that single mutation and can present itself as a double mutation, deletion, insertion, or hybrids. And they can also happen to every type of globin chains, for example, your alpha, beta, or delta. There are many hemoglobin variants. In fact, numbers could be increasing with better molecular detection of the various globin chains. And most of these variants are rare and asymptomatic. For symptomatic variants, most likely the mutation that happens to the globin chain causes chemical issues like polymerization, or we call it cycling, or it alters the binding affinity of oxygen to the globin chain, or it affects the stability of the globin, causing it not to be so soluble, for example, reducing the expression of the globin. And in some instances, like methemoglobinemia, they affect the oxidation state of the iron. So the more common hemoglobin variants would be your hemoglobin S, C, E, and D punjab. Right? These would be the more common variants that could even present in endemic, very endemic in the population. And in such situations, we may sometimes see combinations of different variants. So while the heterozygous variants may appear to be normal, any combination of these variants would then lead to a more severe clinical presentation. And children may then be born with a more severe disease. So now let us look at the normal profile for the human hemoglobins. I would always like to remember the different quantities of the globin chains. There are 4 alpha chains, 2 beta chains, 2 delta chains, and 4 gamma chains. So always remember that there are more alpha genes, there are actually less beta genes. So whenever you have a change to the beta, it will mean more. You will divide the hemoglobin beta genes, right? So in the normal profile, you see a major hemoglobin A peak, okay, a very minor fraction of hemoglobin A2. Occasionally, you do see hemoglobin F being expressed as well, however, in a very low composition. And hemoglobin F expression could be as low as 0.5%. And the normal hemoglobin A2 range percentage would be about 2.2 to 3.2%. Right. So what happens when one of the beta chain is being mutated? So remembering that you only have 2 copies of the beta gene. So with that mutation, you divide your hemoglobin A into 2 peaks in the capillary electrophoretic profile. However, the shifting of the direction of the peak is dependent on the nature of the mutation, because different mutations will present a different chemical change, leading to shifting of the hemoglobin X, the variant peak, in either directions possible. Right? So you could see on the right, like all the possibilities of a hemoglobin beta variant. It's also almost always the case that the hemoglobin beta variant, its peak would have a lower percentage than that of hemoglobin A. One good way to remember this would be that because the hemoglobin variant that's being formed would be less stable, so likely its composition in the blood will be reduced as well. Okay. And in the instances of the beta variant, it's important to note that the hemoglobin F and hemoglobin A2 peaks, the minor fractions, are not split. Why? Because beta gene is only present in hemoglobin A, so you do not split the other hemoglobins. All right, this is the distinct signature profile of the beta globin variants. What if both of the beta genes are being mutated? The same mutation, of course. You would then see one major variant hemoglobin peak. Okay, and you will not have hemoglobin A because there's no normal beta gene to form the normal hemoglobin A. Okay, once again, the position of this variant peak is dependent on its chemistry, so it can be left or right of that of the normal hemoglobin A. So this is a unique feature about hemoglobin when it's on the capillary electrophoresis. So once again, in the homozygous beta variant situation, you do not see the hemoglobin A, and you see entirely shifted position of the mutant hemoglobin A, right? How about the situation of a heterozygous delta variant? So the delta gene, there are only 2 copies of them. So like the beta variant, you would actually see the hemoglobin A2 being split into 2. Once again, the change can affect the chemistry in either ways, that it can shift the peak to the left or to the right. However, because hemoglobin A2 is important for diagnosis of clinical situations like thalassemia, so to consider the hemoglobin A2, the true hemoglobin A2 value, it's important for us to sum up the percentages of the 2 peaks, even though one of them is the variant. Of course, the mutation happening to hemoglobin A2 itself would not be so much of a concern because it would not produce too much of a clinical impact. But the quantity of hemoglobin A2 would be the concern for a diagnosis of conditions like thalassemia. So once again, the true hemoglobin A2 value is a combination of the normal hemoglobin A2 and also that of the variant. So in this instance, you'll be looking at a true hemoglobin A2 value of 2.3%. Now, how about the situation of a heterozygous alpha variant? So recall that for your alpha gene, you have 4 copies of them. And the alpha gene is being used to combine with every other globin type to make the different hemoglobins. So when the alpha gene is being mutated, you affect every hemoglobin type, and you will see a split and shifting of all hemoglobin types. So the alpha variant changes would always show you a capillary electrophoretic profile of many peaks. So once again, the exact shifting of the peaks depends on the change that's done to the variant, depending on the chemistry of the resulting hemoglobin, and that would affect where it shifts to. But when you see multiple peaks, it's important to always think of the possibility of an alpha variant happening. And the same principle also applies if you need to look at your hemoglobin A2 and use it for diagnosis of other conditions. The true hemoglobin A2 value will be that of the variant combined with the normal hemoglobin A2 as well. even though in this situation it's an alpha variant mutation, but you will add on that alpha variant hemoglobin to your hemoglobin A2. So these are the actual capillary electrophoretic profiles of alpha globin chain variants. Okay, you will see a distinctive splitting of all hemoglobin peaks. Another important point about this splitting is, if you would notice by now, that the splitting actually happens in an equidistance on the x-axis. So all the variant peaks, all the alpha variant globin peaks that are being formed, they shift in equidistance. You can attribute this to the same chemical change that's being done to every hemoglobin. Therefore, the splitting and the shifting is equidistant. So whenever you want to make a diagnosis of alpha globin chain variants, this equidistance shifting and splitting would be something that's very signature to alpha globin chain variants. Right. So reminder again, remember that the true hemoglobin A2 value is always the combination of the normal hemoglobin A2 and whatever is the variant, be it an alpha chain or be it a delta chain. So let's take a look at a typical case example. So here you have a male patient, all right, with hemoglobin levels of which is low, 11.9 out of the reference range, and also MCV that's low as well out of the reference range. Okay, so in this instance, the profile looks like the hemoglobin A2 is being split. So very likely there should be a delta variant that's present. However, the delta variant is not supposed to give you a clinical presentation of lower hemoglobin or MCV. So we combine the hemoglobin A2, that the normal A2 value, and also the delta variant composition values. And this combination gives you 4.2%, which is higher than the normal reference range of hemoglobin A2. Also, you see an increase in hemoglobin F, which is very likely indicative of an underlying condition. So most likely, this is a coexistence example of beta thalassemia and also a heterozygous delta variant. Okay, so note that it's very important to consider the true hemoglobin A2 value to detect the underlying conditions. So let's look at examples of the common variants. So this is the heterozygous sickle cell trait. Okay, and you see the in the capillary electrophoretic profile, it's very defined within zone S. Okay, once again, the percentage of the hemoglobin S slightly less than that of the hemoglobin A. So it's also the most common hemoglobin variant worldwide. If this state is combined with other common variants, it can lead to a even though it's a heterozygous condition, it can lead to a more severe disease, providing the sickle cell attributes as well. So it's also important because knowing that every charge-based separation method is only presumptive, it's important to perform your confirmatory methods to confirm on hemoglobin S. Like for example, the second tests, the acid gels on the HPLCs. So this is a situation of homozygous sickle cell. You totally lose the absence of hemoglobin A because there's no normal beta chain to form your hemoglobin A. And hemoglobin S peak would be the dominant fraction. Okay. Of course, there's the elevated hemoglobin F as well. So this is an example of the heterozygous D, hemoglobin D. Okay, although its position is rather near to the sickle cell, but it occupies a different zone. Okay, so in this example, it is overlaid with the control hemoglobin, that you know the different positions of D and S. So this is an example of heterozygous hemoglobin C. So characteristically, always the variant hemoglobin is on a lower percentage than hemoglobin A. Now, hemoglobin E, the heterozygous form of hemoglobin E, even though it's a beta variant, hope you will notice that the hemoglobin E fraction in this case is lower. It's about 25.1%. So uniquely for hemoglobin E, it is a special variant with reduced synthesis. So it does present itself like a mild thalassemia phenotype in patients because it affects hemoglobin E expression, unlike the other common variants that were shown in the previous slides that have a higher percentage in composition. Hemoglobin E is expectedly having a lower percentage, right? And also hemoglobin A2 is increased in the presence of hemoglobin E. So note that it has a thalassemic presentation in a way. Okay, in the instance of homozygous hemoglobin E, once again, you do not have the hemoglobin A fraction. And of course, the hemoglobin A2 is further increased in this instance. So how do we avoid confusion between common and rare variants? Importantly, when we consider every hemoglobin electrophoretic results, we must also associate them with other data that are present for the correct interpretation. And the type of data that we should consider would be every other clinical information that's available, like the age, the complete blood count, the iron status. Okay, because iron deficiency would be a more common problem than hemoglobin neuropathies in some parts of the world. Importantly, to also note if there is any interference from transfusion, okay, to resort to the usage of other methods in parallel to confirm as well. So if the patient comes from a geographical location that has the hemoglobinopathy in endemic proportions, right, you would expect more likely the patient to have the common variants as well. And also importantly, to look at nutrient deficiency and also other parameters like blood smear hemolysis or oxygen saturation. So we have here the 3P rule for the correct interpretation of hemoglobin variant. So first, to look at the profile type. Recalling for the different alpha, beta, or delta variant, there is a different profile type. There's a different signature in the profile type of the splitting of the globin. For beta variant, because the beta gene is only present in hemoglobin A, you see just one splitting of hemoglobin A. For alpha chain variant, you see multiple splitting of all the hemoglobins because every hemoglobin will require the alpha chain. Okay, except for the most abnormal types of hemoglobins where alpha is totally deficient, right, in the thalassemic conditions. Otherwise, if you're looking at the alpha chain variants, every hemoglobin will be split. And because the alpha chains are present in 4 quantities, right, the splitting is not as big as that of the beta chain splitting, right? So you see a splitting with a smaller fraction, but it happens in an equidistant manner, right, to all hemoglobin. Why? Because the change in the alpha chain is the same, for all hemoglobins. In the instance of the delta chain variant, you see that little splitting of the hemoglobin A2. And we're calling that 2A2 value is a combination of both fractions, right? So next would be the position of the peak, the variant peak that's being formed. So in the capillary electrophoresis software, if you were to place your cursor at the peak, it will indicate for you exactly the position of the peak, which is also a signature aspect of the variant to help you identify the variant accurately. Some examples would be for the hemoglobin S, the position, even though the hemoglobin S and the hemoglobin D Punjab are present very closely, of course, they present themselves as different zones in the Electrophoresis software. But if you were to place your cursor at the top of the peak, they give you specifically a different position. For hemoglobin S, it will be 214. For hemoglobin D Punjab, it will be 208. Right? Close but not the same. And of course, with better resolution in capillary electrophoresis, it allows you to separate the bands better so that you do not have the complication of misinterpretation. So likewise, for hemoglobin C and hemoglobin E, if you place your cursor at the top of the peak, you will see a position of 252 for hemoglobin C and 228 for hemoglobin E. Of course, remember that for hemoglobin E variants, the variant peak is much lesser in percentage compared to the other common variants because the hemoglobin E variant has an expressional change, and therefore it resembles like a thalassaemic presentation to some extent. And of course, an increased hemoglobin A2 as well. So the last consideration in the 3P rule would be the percentage of the peak. Right? If the variant percentage is lower than expected, it's important for you to consider that maybe the condition is associated with alpha thalassemia or iron deficiency. Or it could potentially be an underlying transfusion that is missed out. Right? Or it could be a different variant. All right. So if the hemoglobin if the hemoglobin variant, the beta variant, is greater than hemoglobin A, it's important for you to consider that it's possibly a beta thalassemia that's underlying as well. So now let us look at some case reviews to reinforce our understanding of the principles of interpretation. So in this situation, you see apart from your hemoglobin A, which is the main peak in the middle, you see a very large peak on the left. Right, what would these very likely be? Okay, so of course, knowing that there's also a bit of increased hemoglobin F, so most likely the patient has a variant condition that's affecting him significantly. Okay, so this is actually a condition of the presence of beta variant. Right. So remember that the shift in the beta variant position is not confined to only the left or the right, because it depends on the chemical change in the beta gene. It could be either directions. Right? So how about this case? Pretty much the main change would be the splitting of hemoglobin A2. All right. This is very likely the condition of a delta variant. So if you were to combine the two, hemoglobin A2 and the variant delta peak, it will be about 2.1%, so it still falls within a very normal range of hemoglobin A2. The true hemoglobin A2 values are relatively normal. So how about this case? So you see a splitting of the major hemoglobin A peak. Look carefully at hemoglobin A2. You do also see a little hemoglobin B zone, although it's in a very small proportion. So what does this remind you of? A splitting of the hemoglobin to a smaller peak, and this happens equidistant for every different hemoglobin type. Okay, so this is the presence of an alpha variant. Okay. How about this case? You see hemoglobin F increased, hemoglobin A2 is being increased. This is very unlikely. This is very unlikely a variant situation. Okay. This is actually the presence of beta thalassemia because of the increased hemoglobin A2. So in this instance, you also see a splitting of the hemoglobin A2. Okay. So this is a situation of the presence of a delta variant. Okay. So if you combine the two values together, the D zone, the hemoglobin D zone and hemoglobin A2, it's still within the normal range of hemoglobin A2. So what about this case? Okay, so there is the presence of hemoglobin H. Okay, so this very distinctively is a presence of alpha thalassemia. And because alpha genes are being reduced, you do not see that increased hemoglobin A2 as well. So how about this case? You see a major peak in hemoglobin in zone C. Okay, and hemoglobin A2 percentage is within the reference range. Okay, so major splitting, it's most likely the presence of a beta variant. So with that, I come to the end of this presentation, and I would welcome you to post your questions in the chat group. I would also seek your support and help to fill out this survey form so that we can know what are your needs for the webinar and hopefully to make improvements to it as best as possible. Please also feel free to reach out to me after the webinar should you have any questions beyond that. My contact details are present as follows. Okay, I see a question within the chat asking about what's the capillary electrophoresis system you use to detect the hemoglobin variant. Okay, so for all the capillary electrophoretic profiles that you see, we are using the capillary electrophoresis system from Sebia. So currently it is the Capillaries 3. There are two versions. There's the Capillaries 3 Octa. There's also the Capillaries 3 Terra. So Octa refers to 8 capillaries, and the Terra refers to 12 capillaries. So within the system is also the possibility to run your samples high throughput with either the 8 capillary option or the 12 capillary options. You can run them in parallel, right? Yeah, I hope I answer your question. The important thing to know about the capillary electrophoresis is that it is a very high resolution charge separation method achievable. So if you use other methods, you would have to vary the buffer, for example, in charge separation. But for capillary electrophoresis, because the sample is separated within a very fine capillary, there is only one buffer that is involved in that separation. So that's why you see very clearly resolved peaks in the examples just now. Okay. As far as there is a substantial change to the hemoglobin, the capillary electrophoresis method will be able to resolve these two peaks very well. And also because the capillary is very fine, it's even finer than that of our hair. So the profile of the capillary migration will be very flat. Okay, this is a phenomenon because of the very narrow capillary diameter. Okay, I see another question. Thank you for your question. Can we use it as a confirmatory test, or it is just a screening test for hemoglobin variants. Okay, so I want to say that it can be used as both. If you want to use it as a screening, it's possible as well. If your lab already have an existing method, the capillary electrophoresis method can definitely be used as a confirmatory test as well. It's a very high resolution testing method, so it gives you very good clarity about your results. For example, you will not see, hemoglobin E and hemoglobin A2 migrating in the same area. It separates them clearly, as we have seen in the profile earlier. Thank you very much for your question. Thank you. The Sebia's capillary system is also has a broad testing menu as well. So even beyond that of hemoglobin testing, you are able to look at other things like hemoglobin A1C, for example, as well. And because it is good for the separation of hemoglobin, when you do a hemoglobin A1C testing, you also see the highly resolved hemoglobin types. So it allows you to detect hemoglobinopathies even when you're doing an A1C testing. So there are instances where patients' underlying conditions are being detected, or you would know that the patient has an underlying hemoglobinopathy that would affect the reliability of the A1C results. And the system can also be used for myeloma-related testing to look at seroprotein as well. Okay, so with that, we have kind of reached the end time for the webinar. Thank you very much for taking time to attend this webinar. And I look forward to questions that you might have after this session. Please feel free to contact me. Right, I would like to wish you a very pleasant day ahead and take care and all the best. See you soon again.